Hello students, welcome back to our channel Diksha Karnataka. So your COMEDK 2024 examination is approaching. So in this video, we will do the complete revision of the inorganic chemistry. Okay, so I'll be covering all the important or inorganic chemistry chapters. I'll be discussing the important topics and the type of questions that is asked also I'll be discussing. So if you watch this video, you can revise the complete inorganic chemistry and you can expect like easily 12 to 15 questions from this all these four topics because all are high weightage topics. So let us start here, and you will be also getting the PDF of this in our WhatsApp channel. So join our WhatsApp channel. The link will be given in the description section of the video. Okay, so please sit with the notebook and a pen and note down all the important concepts, all the important exceptions, and whatever I tell, just note it down and revise it thoroughly for your COMEDK examination. Okay, so one of the very important video, complete revision of inorganic chemistry. So let us start now with the, so in this video we'll be discussing the four important chapters, that is coordination compounds, DNF block elements, chemical bonding, and classification of elements. Okay, so let us start with the first chapter, that is coordination chemistry. It's a high weightage topic from your PU2, right? So you can easily expect 3 to 4 questions from this chapter. So what are the important topics in this chapter? First, let us see them. So first is your Werner's theory. Okay, so next is your important terms. Will be like questions are asked from these important terms also. Next is nomenclature, very important. Then you have isomerism, then you have bonding theories, and the last is bonding in metal carbonyls. So if by seeing this list I'll say which is the most important thing, then you must mark about Werner's theory, isomerism, nomenclature, and bonding in carbonyls. Bonding in metal carbonyls questions are not asked, but we never know, the question may be asked. So just a very simple concept, we can just revise it once. Okay, so now let us start with the Werner's theory. So according to Werner's theory, in a coordination compound, there are two types of valency. One is your primary valency and secondary valency. So what are the properties of primary valencies? They are ionizable. They can be satisfied by negative ions. And what is, like if someone asks you what is primary valency, it is nothing but the oxidation number of the metal. Okay. Now coming to secondary valencies, these are non-ionizable, satisfied by negative or neutral molecules, and the this is like what is secondary valency? It is the coordination number. Okay. Now how questions are asked? Will they ask you the definition of this? No, they will ask you like, suppose a compound will be given. For example, we have a complex like this, any metal, and then you have CO ligand 4 and then X ligand and then Br3. Then how many ions were produced from here? Right, so this complex will be 1 ion and then 3 bromine will be another ion. So total ions produced will be 4. So such type of questions are asked. And the question like about AgCl, so prepare this AgCl concept. Okay, so when they react with when you react a complex with AgNO3, how many moles of AgCl is produced, and based on that we can tell how many chlorines were outside the complex and how many chlorines were inside the complex, right? So such type of questions, application based questions, are asked from Werner's theory. Now let us go to the next topic, important terms. Which important terms are there? So ligands, there's like this, just for you should know that number of ions or metals that is bonded to the central atom. Now denticity is important. Here you should know the number of ligating groups in a ligand, how many how many sites are there which can donate the electrons to the metal. Now, if you see unidentate ligand, here examples are Cl minus, H2O, NH3. Didentate ligands, your examples are ethane 1,2-diamine, which we write as En. Then polydentate ligands, you have the example of EDTA. Okay, so here you should remember EDTA is hexadentate ligand. Okay, next coming to ambidentate ligands. So what do you mean by ambidentate? It means like there will be two donating sites in the ligand, but at a time, or at least like at one point of time, only one will donate. Okay, so your examples are SCN and NCS. Your example is NO2 and NO. So you can just know like questions can be asked which of the following is ambidentate ligand, what is the denticity of these ligands. Okay, so on the basis of denticity, you should know the examples. Now coming to coordination number, so the number of ligand atoms donated to the metal directly bonded is called as the coordination number. So from here also you can see cobalt is bonded to 6 ligands, so the coordination number is 6. Now homoleptic and heteroleptic complex, these are very simple concept. So if only one kind of ligands are there, then it is homoleptic. If more than one kind of, so sorry, this one NH3 whole 4 and Cl2. Okay, so if this we have more than one type of ligands, then we call it heteroleptic. Okay, next coming to nomenclature, very very important. So I will briefly explain the rules and then we will do two examples. You can practice nomenclature examples from NCERT exam in the chapter, it is there inside the chapter, in the text questions also there, in the in-text questions also there, right? So practice nomenclature thoroughly. Okay, so if I tell like in coordination chemistry, what you must know is your nomenclature. Okay, so coming to that, first rule is the cation should be named first and then the anion. So whether cation is a complex or anion is a complex or cation is auxiliary ion, doesn't matter. First cation, then anion. Now the ligands are named in the alphabetical order. Okay. So in the complex, first the ligands will be named and then the metal will be named. Name of the anionic ligands in ending it with O. Those of the neutral and cationic ligands are same expected for water, amine and carbonyl for CO and nitrosyl for NO. Okay. So what does it say? The ligands, okay, the name of the ligands will generally end with O for negative anionic ligands, and for neutral ligands there are special names, like for water it is aqua, for NH3 it is amine, for CO group it is carbonyl, and for NO group it is nitrosyl. Okay. Okay, now coming to this one, if more than one ligands are there, then what prefix we should use? Mono, di, tri, like that we have to use. Now if the name of the ligand contains more than one name, then we have to use bis, tris and tetrakis for giving you the number of ligands present. Next rule is Roman numeral in the parenthesis. So after the metal is written, its oxidation state is written in Roman numbers in brackets. Okay, which type of brackets? Like this bracket. Okay, next, if the complex is a cation, so I told you complex can be cation also, can be anion also. So if the complex is a cation, then the metal is named as same as the element. For example, if the metal is iron, then it will be iron. The metal is cobalt, it will be cobalt. But if the complex is anion, okay, the anion part is the complex, then the metal name should end with ATE. Okay, that is very important. Now let us see one example here. You can see this compound. Okay, so this, in this case, the complex is your cation. Okay, so here first you have to name the ligands. So we have here 3 aqua and we have 3 amine group, right? So based on your alphabetical order, first amine will come. So triamine, triaqua. Then since complex is the cation, the metal name will remain as it is. So chromium. Okay, then 3. Then we have chloride. Okay, here this should not be written as trichloride. For auxiliary ions, there should not be any suffix or prefix required. Now if you come to this one here, this is a ligand with more than one name, ethane 1,2-diamine. So 3 are there, so we have to use the word tris. Okay, tris ethane 1,2-diamine, cobalt, then oxidation state and then sulfate. Here also you need not write trisulfate, should not be written. Okay. Now coming to isomerism, next important topic. So isomerism is of 2 types. First is your optical isomerism and then is your structural isomerism. In optical isomerism, we have geometrical isomerism and stereoisomerism. Geometrical isomerism, you know, cis and trans, and in stereoisomerism, enantiomers are there, right? Now in structural isomerism, we have linkage, ionization, coordination and solvent isomerism. Very, very important topic. Okay, now let us first see geometrical isomerism. So in geometrical isomerism, if you see, if the same ligands are on the same side, we call it cis. If the ligands are on opposite side, we call it trans. Now you can see here, this is for coordination number 4. Okay. Now if coordination number 6 is there and the ligands are of the form like Ma4B2, you can see if the 2 chlorines are opposite, it is trans. If 2 chlorines are lying in the, like, are not opposite to each other, this is the cis geometry. Next, coming to this one is very important, Ma2B2 type. Okay, where this is a bidentate ligand. Okay. In this case, you must remember the cis form of this one is optically active. Okay, cis form of this one is optically active. We'll see that also. So cis form, you can see 2 chlorines are opposite to each other, that is trans form, and when the 2 chlorines are nearby to each other, that is your cis form. Okay. Now coming to the next question, next topic, that is stereoisomerism. So if you have the mirror images are non-superimposable mirror images, then they form enantiomers, right? So you can see here, this is like a form COEN whole 3. So these 2 are non-superimposable mirror images, so they will be our enantiomers. And now if you see this one, AA2B2 type, I told you, the cis form will be your optically active, trans form will be will not be optically active. Okay. Next, seeing the next one, structural isomerism. So here you should know what is linkage isomerism. For linkage isomerism, we need ambidentate ligands. Okay. So if NO2 is there, what is its linkage isomer? So CO, NH3, 5, ONO, Cl2. Okay. Now coming to coordinate isomerism. In coordinate isomerism, what happened? Ligands get exchanged. So what will be the coordinate isomerism for this one? CO, I'll write CN whole 6 and we have CR NH3 whole 6. Okay. Now coming to ionization isomerism. In ionization isomerism, when you put the compound in the water, if different ions are produced, then we call it as ionization isomerism. Now in this case, what we'll get this complex as 1 and Br minus as another ion. Here we'll set this complex as 1 and sulfate as another ion. So formula is same, but in water we are getting different ions, so we call it as ionization isomerism. In solvent isomerism, very easy. Water should be there as a solvent, right? So you can see here we have water and here this water can come out and Cl3 can go out. So water can be coming like inside the complex and outside the complex you can interchange, then we will get a solvent isomerism. Okay. Okay. Now coming to bonding theories. Okay. So what were the different theories that describe the coordinate bond or coordination bond? So first theory that came was your valence bond theory. According to valence bond theory, what happened? The n-1d, ns, np, ns, np and nd. Okay. So these orbitals can participate in the bond formation. Okay. So these orbitals undergo hybridization to yield a set of equivalent hybrid orbitals such as octahedral, tetrahedral or square planar. So here are the hybridizations. You must remember, if the coordination number is 4, we have two types of hybridization, that is sp3 and dsp2. So you can see here there are two types of combination. I'll write. See, you can see if we have n-1, so I'll write here. See, for sp3 we need ns and np orbitals to combine. For dsp2 I need n-1d, ns and np orbitals to combine. For sp3d2 we need ns, np and nd. Okay. And for sp3d, now same for sp3d2, but for d2 sp3 we need n-1d, ns and np orbitals. Okay. So these are the geometries. Now what are the geometries produced? You can see for coordination number 4, we have two types of geometry, tetrahedral and square planar. For sp3 it is tetrahedral, for dsp2 it is square planar. For coordination number 5, sp3d, it is trigonal bipyramidal. For coordination number 6, sp3d2 octahedral, d2 sp3 is also octahedral. So whenever you are using n-1d, we call it inner orbital complex. Okay. Okay, now let us see. These are the 4 examples of the compounds that are given in your NCERT book. Okay, so please remember these examples thoroughly so that in exam you did not have to calculate and find out everything. So for cobalt NH3, it is a strong field ligand. So that is why we will get D2sp3 hybridization. Shape will be octahedral since the coordination number is 6. And since it is a strong field ligand, pairing of electron will take place. It will be diamagnetic, right? Now if you see here, next one is COF6 3-. It is a weak field ligand, right? But coordination number is 6. So we will get octahedral geometry. Weak field ligand means outer orbital complex sp3d2. So I'll write here, this is inner orbital, this is outer orbital. Okay. Next, the magnetic property will be paramagnetic because it has unpaired electrons. Now if you see NiCl4 2-, this is sp3 hybridization. Again, this is outer orbital complex, tetrahedral and paramagnetic. And in NiCN4 2-, so there is no concept of outer because d orbital is not involved. Here it is dsp2 square planar and diamagnetic. Okay. Next one we'll see. So what does crystal field theory tells us? So next, after valence bond theory, the next bonding theory is crystal field theory. So in crystal field theory, this one a question was asked. You should know metal ligand bond is considered to be ionic arising purely from electrostatic interactions between the metal ion and the ligand. Okay, so this point you should remember. According to this crystal field theory, the metal ion and ligand has an electrostatic force of attraction, because of which we consider them as an ionic bond. Okay, next. So what happens when ligand approaches to the ligand approaches the metal, the d orbitals split to reduce the repulsions. So splitting of d orbitals depends on the strength of the ligands. Okay, the splitting can be more, splitting can be less, depending on the ligands. Okay. Now coming to this, so we have crystal field theory, crystal field splitting in octahedral. So what happens first, initially all the 5 d orbitals are degenerate. Now when the ligands approaches to reduce the repulsion, they go in this way. Okay, so 3 orbitals come here and 2 orbitals go down. You can see in the diagram here. If it is visible, these 3 orbitals are called as your T2G orbital, dxy, dyz and dxz. Okay, so what are that? I'll write here dxy, dyz and dzx. Now similarly, out of 5, 3 went down, so 2 will be up. So these 2 are your dx square minus y square and dz square, right? You can see here. Now you should also remember the values. Okay, so how much decrease is there? So how to remember? See, total there are 5 orbitals. Okay, so here 3 is there, 3 has come down, so this will be minus 2 by 5 delta O, and here there is 2, so it will be 3 by 5 delta O. Okay, so please remember, this is plus, this is minus. Okay, next is your crystal field splitting. Okay, so this is the same one which we have explained. Next is your crystal field splitting in tetrahedral complexes. So if you see in tetrahedral complex, the opposite will happen. So here 5 orbitals were there, right? After this one, 2 will go down and 3 will go up. And here we do not use the word T2G. G is not used. So it is only called T2. Sorry, this one is called E and this one is called T2, right? So here the orbitals are your dz square and dx square minus y square, and here it is dxy, dyz and dzx. Okay, so crystal field splitting in tetrahedral is not much asked in the question, but in octahedral complex the splitting is very, very important. Okay, now coming to, okay, here I want to discuss one more thing about the how to write the electronic configuration in strong field and weak field. So very important, see here, if it is a strong field ligand, okay, then splitting will be more. Okay, splitting is high and pairing of electrons will not take place. Sorry, pairing of electrons will take place. Okay. Now for D1, D2, D3, there is no configuration change whether it is a strong field ligand or it is a weak field ligand. But for D5, D4 to D7, you have to be very careful. Now we will discuss that. Suppose D4 is there, okay, strong field ligand and weak field ligand. So here you imagine, here we have strong field ligand, so splitting will be more. Okay, so we'll draw here. In strong field ligand, the splitting will be more. Okay, and in weak field ligand the splitting will be less. Okay, so now this is strong field ligand and this is weak field ligand. Okay, so now we have here 3 orbitals, here 2 and here also 3 and here we have 2. Now D4 is there, right? So how you should not remember it, you have to understand it. D4 is there means 4 electrons, 1, 2, 3. It cannot go there because it requires more energy, so it will pair up here. So D4 in strong field will be T2G4, right? But in weak field, what will happen? 1, 2, 3. It is very less energy gap. It can easily go there. So here it will be T2G3 and EG1. Now similarly D5, if you see, 5th electron will also come here. So we will get T2G5 and for here we will get T2G3EG2. Now if you see D6, again the 6th electron, 5th electron came here. 6th electron will come here. So we will get T2G6. Now for weak field ligand, if you see 1, 2, 3, 4, 5 was there and now 6th electron will come here. So we will get T2G4 EG2. Now for D7, if you see, already T2G6 has been there. Now T2G7 will come here, right? So 1, 2, 3, 4, 5, 6, 7th electron has no other option. It has to go there. So we will get here T2G6 EG1. Now if you see for this one, 1, 2, 3, 4, 5, 6 and 7 I can fill here. So I will get T2G5 and EG2. Okay. So this D4 to D7 configuration for strong field and weak field you have to remember. Next, color in coordination compound. So very basic thing you have to remember. There's no like the only thing you have to remember, if there is unpaired electron, okay, if there is unpaired electron then it will be colored, okay, and if there is no unpaired electron then it will be colorless. How will you know whether it is colored or not? For that you must know the configuration, okay. Now the color is due to DD transition, okay. Next, coming to bonding in metal carbonyls. I told you this is not a very important topic, but we can understand in a very short way. So first of all, there is a metal carbon bond. So there is a metal carbon bond, okay. So carbonyl donates electron to metal. That is what is done by every ligand. Every ligand donates electron to the metal. What special is here? The speciality is the metal also donates back electrons to the carbon, right? So the metal carbon bond in metal carbonyls possess both S and P character. So this is sigma bond and this is pi bond, okay. Now the MC sigma bond, the sigma bond which is formed is due to the donation of electrons from the ligand to the metal, is formed by the donation of lone pair of electrons on the carbonyl carbon into the vacant orbital of the metal, okay. Now MC pi bond, okay, this pi bond is donated by metal to the carbonyl, is formed by the donation of a pair of electrons from a filled d orbital of metal into the vacant anti-bonding orbital of carbon monoxide, right? So you can see here this one, okay. Here sigma bond is from carbonyl to metal and pi bond is from metal to carbonyl. So anti-bonding orbital is used, okay. So these were the important topics in coordination chemistry. So what you have to focus, only one day or like 1.5 days left. So focus on your nomenclature, isomerism and d orbital splitting. These are the 3 important topics that you must clear, okay. So now let us go to the next important topic, that is D and F block. So here we will be discussing the important configurations, important trends, important exceptions, okay, and like the physical properties. Different D and F block, they show different physical properties. What are the reasons for that? The questions can be asked from there, right? So let us quickly go through this chapter. What are the topics? First, electronic configuration, okay. This is very, very important, okay. Without doing electronic configuration, you cannot solve even a single easy question from this one. You need to know the magnetic property, you need to calculate the color, whether it is color or colorless. Everything you can do only if you know the electronic configuration, right? So please remember scandium to zinc, all the electronic configuration, very, very important, okay. Next, important trends we will discuss. Next, physical properties and why this physical, what are the reasons for these physical properties, and then we'll discuss about the F block elements, okay. Okay, so the electronic configuration is already there, so nothing to discuss here. You must remember here. So just I'll tell, chromium and copper has a special electronic configuration. 3d4 4s2 was the expected value, but due to the half-filled electronic configuration, what happens? We get 3d5 and 4s1. Similarly, for copper we have 3d9 and 4s2 is the expected electronic configuration, but the observed is due to 3d10 4s2, so that it becomes a fully filled d orbital, okay. And we know fully filled electronic configurations are very stable. Next, one more thing here is, what is the general electronic configuration? n-1 d 1 to 10 ns 1 to 2, okay. So n-1 d 1 to 10 ns 1 to 2. Okay. Next, so coming to the first trend, that is your atomic radius. So first of all, atomic radius decreases rapidly from column 3 to 6. So that is from your up to scandium to chromium, the atomic size decreases. Then it remains constant from 7 to 10. So you can say almost from chromium to nickel it is constant, and then it starts rising from 11. So I can write here from scandium to chromium, then from manganese to nickel, and then copper to zinc, it increases, okay. Okay. So now what is the reason for that? Here what happens? Here the effective nuclear charge is more powerful, okay. Here what is like the effective nuclear charge, okay, and the repulsion, the d electron repulsion, both are d electron repulsions are balanced out. And in the last one, if you see, the d electron repulsions are more dominating than the effective nuclear charge. So if you can understand, effective nuclear charge, okay, wants to try to pull the electron towards itself and wants to reduce the size of the atom. And since as we go from the period, the d electrons are getting filled, so there will be inter-electron repulsions between the d electrons, so that wants to expand the size. So there is a conflict between them. So when we are going initially up to, you can say up to chromium, the effective nuclear charge is the winner. So what is its effect? It wants to reduce the size, right? So till chromium it will reduce the size. Now if you go in this region, you can see there is a, like, this region is almost constant, right? The size is almost constant. So at this point what is happening? The inter-electronic, the d repulsions of the d electrons, and we have this effective nuclear charge, they're almost balanced out on each other. Now as we go around copper and zinc, d10 electrons, right, they're completely filled, more repulsion, so they are more dominating and the size keeps on increasing. Okay, next we'll go ionization energy. So ionization energy increases with the increase in the atomic number up to Fe. So as the size decreases, the ionization energy will increase. Okay. Next, in cobalt and nickel, the increasing sharing of d electron compensates for the atomic number increase, resulting in the decrease in the ionization energy. So again, as we say, from cobalt to nickel, as the d electrons start filling, so the effective nuclear charge decreases. So that is why the ionization energy decreases. Then again, copper and zinc shows increasing ionization energy, because here it is completely filled d10 orbital, right? So removing of electron from completely filled orbitals is again very difficult. So that is why from nickel to copper it keeps on increasing. Okay. Next, metallic character and hardness. So the d block elements have the metallic character like high tensile strength, malleability, ductility, electrical and thermal conductivity, metallic luster, crystallize in BCC. So these are basic things, we need not focus here. Here it is important. They are very hard and have high enthalpy of atomization and low volatility, except copper, right? So copper is having 3d10 electronic configuration, so it doesn't have like metallic bonding is very weak, so that is why it is enthalpy of atomization is very low. Now hardness increases with the number of unpaired electrons. So more is the number of unpaired electrons, more will be the metallic bonding and more will be the hardness of the metal. Now as you see, chromium, molybdenum and tungsten, they are having the highest number of unpaired electrons, so they show the highest, they are the hardest metals, and they also have very high melting point and boiling point. But if you see zinc, copper, zinc, cadmium and mercury, they are having like no unpaired electrons are there, so no metallic bonding, and that is why they are very soft metals. Okay. Next is your oxidation state. So if you see, so they show variable oxidation state due to the participation of n and n-1 d electrons. So why both the orbitals participate? Because of less energy difference. Okay. Now the higher oxidation states will be stabilized by fluorine and oxygen. The lowest oxidation shown is +1. Highest oxidation state in the entire 3D elements is shown by +8, that is your osmonium. Then this you have to remember, very important, which are your basic oxides, which are your amphoteric, and which are your acidic oxides. So if you remember, like a general thing, if oxidation state is low, then it is basic. Okay. If oxidation state is somewhere in medium, then it will be amphoteric, and then oxidation state of if is very high, then it will be acidic in nature. Okay. So you have to remember amphoteric, especially remember all the examples, very important, because they will be asking like which of the following oxides are amphoteric or basic or acidic. So you have to remember as many examples as you can. Okay. Now coming to the next one, electrode potential. So depends, so here you have to know electrode potential like depends on what three factors? It depends on sublimation energy, ionization energy, and hydration enthalpy. Next, one more thing, copper is the only element with a positive electrode potential of 0.34 volt. So this one also you remember. Okay, next coming to physical properties. Okay, we discussed about the chemical properties. Now some physical properties of transition elements. So first is density. Okay, so density increase remains almost the same and then decreases along the period. So if you know, density formula is what? Mass by volume. Volume we can, since it is pair, we can like 4/3 pi r cube. Okay, so density is inversely proportional to radius. So initially if you see the radius was decreasing, if radius was decreasing, then if radius will decrease, then density will increase. So initially it decreases, then radius remains constant, density remains constant. Then towards the end, radius increases, so volume will increase, so density will decrease, right? That is what happening. Now here something you can remember, scandium in the third 3D series, okay, scandium has the lowest density and copper has the highest density, okay. And then copper has the highest density, it has different reasons, like, but you should remember the elements. Then osmium and iridium, these are the highest density among all the D block elements, okay. Next we come about melting point and boiling point. This is also very important to understand. If the metallic bonding is very strong, melting point and boiling point will be high, and metallic bonding depends on the number of unpaired electrons. So chromium, molybdenum and tungsten have very high melting point because they have stronger metallic bonding, okay. Now manganese and technetium, what happens, although they have unpaired electrons, but they are half filled configuration, right? So they are very stable, they are not involved in metallic bonding, so they have low melting point and boiling point. Now zinc, cadmium and mercury, because they have no unpaired electrons, they cannot undergo metallic bonding, so they also have the lowest melting point and boiling point in their respective series, okay. Now coming to colored iron, so this is very easy concept. Due to DD transition it happens, if there is no unpaired electron they will be colorless. So questions are asked, which of the following are colored, which of the following are colorless, so you can easily use this concept and find it out. Next is, we know that this D block elements can form complex. So what are the reasons for that? They can know small ionic size because they have high charge and they have availability of d orbitals. So you should know these reasons, like question can be asked like 3-4 factors will be given, which factor contributes for complex formation, right? So you should know these basic things. Next, similarly, catalytic property is due to the vacant d orbital and they can exhibit variable oxidation states. Alloy formation, this is because of all the transition elements have almost similar atomic radii, so it is easy to mix them. Now interstitial compounds, so they so whenever you have like crystal is there will be some spaces or voids will be there, and that voids are filled with non-metallic items, like here we have nitrogen, hydrogen, oxygen, carbon, okay? So when they enter and they form interstitial compounds. Okay, next is very important, this one, important compounds in the compounds in DNF block. So first is your potassium dichromate, that is K2Cr2O7. So if you see here, the starting material, you should remember, many times this question is asked, that it is prepared from chromite ore, okay, the formula and the name, iron chromite ore is there. So this one is converted to sodium chromate, then sodium chromate is converted to sodium dichromate, then sodium dichromate is converted to potassium dichromate. Exact relation, the equation no need to remember, just remember the starting materials and the products of each step. Okay, next is your structure. So here question is asked like, are all the bonds equivalent or not in dichromate, right? So you can see that these 3 bonds undergo resonance, so they are equivalent, but these CRO are not equivalent, right? And the chromate ion and dichromate ion structure. Next, we'll go to the next important compounds, that is KMnO4. So here also you can see the preparation, manganese oxide, KOH. So the starting material is manganese oxide and it gives you potassium manganate, and then from potassium manganate we get potassium dipermanganate, okay? So these 4 structures you should remember, or the name you have to remember. Next, coming to, yes, lanthanides, very, very important. Electronic configurations are there, but I'll recommend or I'll suggest you to remember all the electronic configuration, but still if you have no time or you're not able to, certain electronic configuration that you must remember is your lanthanum, cerium, okay, and then europium, gadolinium, and then you have the ytterbium and lutetium, and yes, these elements, electronic configuration, please remember, okay, very, very important electronic configurations. Now, so what is the general electronic configuration? Here also it is written 4F 1 to 14, 5D 0 to 1 and 6S 1 to 2, okay. Now coming to the oxidation state, so this is very important slide. So common oxidation shown is +3, okay, but in certain cases it can show +4 and +2 also. So what are there if we can get a noble gas configuration? So if you see cerium, okay, cerium has 4F1 5d1 and 6s2. So if it loses these all electrons, it will have a noble electronic configuration of xenon, right? So that is why here it can show +4 oxidation state. Now it can also show +2 oxidation state if it is getting a half filled configuration. So europium and terbium 4+. So if you see europium, if you see 4f7 and 6s2, so +2 will give you 4f7, right, which is plus 4f7, which is your exactly half filled, so that is why it can show. And we have here 4f terbium is 4f9 and 6s2. So if it loses 4 electron, 2 electron will go here, 2 electron will go here, we will get 4f7. This is also, in that case also they can show +2 and +4 state. Now next one is your Yb2+. If it is a fully filled level is also there, then also it can show, but general oxidation state is +3. In certain cases it can show +2 and +4. Okay. Now let us see the next one. What about atomic radius? So we know from lanthanum to lutetium that lanthanide contraction is there. Why? Due to the poor shielding effect of 4f orbitals. So the size increases steadily. Okay. Now what are about colored compounds? They are silvery white in color. They are all colored compounds due to FF transitions. Now this is again very important slide. Lanthanide contraction and its consequences. We have already seen the causes. What is the consequences? The atomic size, okay, of the fifth period and sixth period elements are almost same. So example you have to remember zirconium and hafnium and Nb and Ta. Okay. Next one is your due to this what happens? Due to this they have the similar chemical properties, so it is very difficult to separate them. And the last one is their basic strength. This is very important. Lutetium is the last one. Okay. So effective nuclear charge is very high. The electron pairs are very tightly held. It is very difficult to donate. So it will have the least basicity. Whereas lanthanum size or the effective nuclear charge is less. Its lone pair can be easily donated. So its basicity is less. Okay. It is high. Okay. So now let us see the next chapter from your PU1. This is a very high weightage topic and very easy question. The questions are asked from a certain section of the chapter, not the entire chapter, but we'll discuss the whole chapter. But I'll also be telling you which chapter or which topics you must focus, from where the questions are must asked. Okay. So let us start with the next chapter, that is chemical bonding and molecular structure. Okay. So first let us see the topics here. There are a lot of topics in this chapter, but again the important topics are very few and very scoring topics. First is your Lewis structures, how to draw the Lewis structures. Second, octet rule and its exceptions. Then we have formal charge calculation, ionic bond, covalent bond, Vesper theory, Fazan's rule. Then we have dipole moment. Then we have hydrogen bonding, valence bond theory, and then we have hybridization, and then bond parameters, and then molecular orbital theory. I'll be telling you now which are the most important one. So first important one is covalent bond. Formal charge calculation, just will practice some formulas and we can do it. Dipole moment is not very important, but sometimes questions are asked like which has a net dipole moment, so you should know where it is cancelled and where it is not cancelled. Then hydrogen bonding, also 1 or 2 questions have been asked like intermolecular and intramolecular hydrogen bonding. Valence bond theory is as hybridization is important. Valence bond theory, nothing much is there. If you know Vesper theory, then just have to understand the concept. Bond characters is important. Molecular orbital theory is very important. Okay. Now let us start with Lewis structure. So just what is Lewis structure? Drawing, you represent the bonds with a line, the lone pairs, the non-bonded electrons with the dot. So we calculate the total valence electron, and then we assume that every element has an octet rule, satisfies the octet rule, and then we fill the electrons, right? That is what is Lewis structure. Now octet rule, what is it? According to octet rule, every element wants 8 electrons in its valence shell to gain stability, right? Now there are some exceptions to this that you should know. So that species like which have odd number of electrons, NO and NO2, they cannot, their octet is not satisfied. Then we have incomplete octet and we have expanded octet. So those elements where the number of electrons of a central atom is less than 8, and there are some elements or some compounds where the number of electrons of the central atom is more than 8, right? So expanded octet is more than 8, incomplete octet is less than 8. So if you see this one, BCl3, okay, boron has your 3 electrons in the valence shell, right? So it forms bond with 3 chlorine. So if you see, there are total 6 valence electrons for boron, whether it should be 8, right? So that is incomplete octet. Now if you see here SF6, right, sulfur has 6 electrons. So we'll draw like this, SF. So 6 valence electron forms 6 bonds with 6 fluorines. So the total number of electrons we get is 12, right? So you should remember second period elements, okay, will not show expanded octet. Will not show expanded octet because they do not have empty d orbitals. The third period elements, you can see phosphorus, sulfur, these are all third period elements. They can show expanded octet because they have availability of d orbitals, okay? Now let us go next. Formal charge calculation, very, very important. We'll do one example on this one. For example, ozone structure, if you know, resonating structure of ozone is this one, right? So your task is to calculate the formal charge on all the oxygen, O1, O2 and O3, okay? So we don't know this one, we'll draw. So here you can see 1, 2, 3, 4. So 5, 6, 7, 8. 8 electrons are satisfied. 1, 2, 3, 4, 5, 6. So 7, 8. And here 1, 2, 3, 4, 5, 6, 7, 8. Okay. Now formal charge calculation formula is for every element the total number of valence electron. Okay. Total number of valence electron minus the total number of lone pair of electrons. How many electrons are there in the lone pair? And then plus to the total number of bonds. Means this is negative only. This total you have to add and then subtract from the total valence electron. Now we will do for this one, for O1. Oxygen has how many valence electron? 6, right? So it will be 6 minus, then you see how many lone pair of electrons are there. 1, 2, 3, 4, not pair. How many electrons you have to calculate? So 6 plus 2, that is 4. Okay. Then here we have how many bonds are there, not bond pair of electrons, only bond pairs, So we have 2 bonds, right? So this one we will get 0. So formal charge of this oxygen is 0. Okay. Now let us calculate for O2. This is not oxygen, okay, second oxygen. So there are 6 valence electron minus. How many lone pairs of electrons are there? 2, okay. Then how many bond pairs are there? 1, 2 and 3. That is 6 minus 5, that is 1. So we will get plus 1 here. Now if we have O3, you can see 6 valence electron minus. How many are there? Total number of lone pair of electrons, that is 6. And how many bonds are there? That is 1. Okay, 6 minus 7, we have minus 1. Okay, plus 1. So here it is 0, plus 1, minus 1. Okay, that is how you can calculate the formal charge. Now coming to ionic compounds, very shortly we can discuss how the ionic compounds are formed by the transfer of electrons. Ionization energy, so the metals has to release 1 electron, the non-metal has to gain 1 electron, and when they combine, lattice energy is released. Now what are the conditions? So ionization energy of the cation should be low. Very easily we should be able to release the electron or remove the electron from the cation, and high electron gain enthalpy of the anion and high lattice energy, right? So means the anion should be able, or the non-metal should be able to gain the electron, it should become stable, it should release more energy, and when the cation and anion combine, there should be loss of energy so that the molecule is stable, so lattice energy should be high. Okay. Now coming to covalent compounds, again what is covalent compounds? It is formed by the sharing of electrons. The electrons which participate as called bond pairs, which do not participate as are called as lone pairs. This is very important because Vesper theory is completely based on lone pair bond pair, right? Okay. Now coming to Vesper theory. So what does Vesper theory says? The shape of the molecule is determined by the repulsions between all the electron pairs present in the valence shell. These electron pairs can be bond pair, can be lone pair. Okay. So the order of repulsions you should remember: lone pair, then lone pair, bond pair, and then we have bond pair, bond pair. Okay. Now repulsions among the bond pairs is directly proportional to the bond order and electronegativity difference between the central atom and the other atoms. Okay. Yes, this is the topic from where definitely every year we get questions. A lot of questions are asked. This table, everyone, whether you study chemical bonding or not, this table everyone should remember and go to the exam. Definitely a question comes from here. The structure and the geometry you must remember. So if electron pairs are 2, then it will be definitely 2 bond pairs. The shape is linear, geometry is linear, and the example you can remember. Next, coming to 3 electron pairs, it has 3 bond pairs and 0 lone pair. Then we'll get trigonal planar. Shape is also trigonal planar. Examples are BCl3 and BF3. Now if we have two bond pairs and one lone pair, then it is a bent shape. Example is SO2. Then we have four lone pairs and four bond pairs and zero lone pairs, then it is tetrahedral CH4, and then 3 and 1 you will have pyramidal, 2 and 2 you will get bent. Now if you have 5 electron pairs, what are the possibility? 5 0 4 1 3 2 2 3, right? So here we'll get trigonal, bipyramidal, seesaw, T shape and linear. This is important, this is important. Square pyramidal, square planar. Okay, these are all important geometries, so please remember them. Then for coordination number 6, we have 6 0 5 1 and 4 2. This table, please take a screenshot. Remember, it is there in the NCERT book also. Very easily available and very important table. Okay. So this is just I'll discuss, like I have discussed, you have to remember the examples properly. Okay. Now next one is your Fazan's rule. So here the questions are asked, like they will give you the compounds and you have to arrange them in the increasing or decreasing order of your like covalent nature. Okay. So for more, if the covalence is favored by, when we can say that the molecule is more covalent, if the cation size is smaller, anion size is larger, and the cation or anion, anyone should have the more charge should be more. Okay. Like for example, if we take for example NaCl, okay, CaCl2 and MgCl2. Okay. Now if you see here, first of all the anions are same, you have to check the cations, right? So cation size should be smaller. So if you see, they are in the periodic table like this: sodium and magnesium and then calcium. So the smallest size is of magnesium, right? So magnesium will be the least covalent nature, or the compound with the least covalent with the most covalent character. Okay, so like this you can find the order. And now coming to dipole moment. So dipole moment, you know the formula is Q into D. Okay, dipole moment formula is Q into D. And then what else is there? Here you have to know the units, that is D by units. And there's more important here, formula based questions are not asked, like whether the compound is having a net dipole moment or not. Like for example, they'll ask you 1,4-chlorobenzene and 1,2-dichlorobenzene. Okay. This question was asked in the previous year also. Okay. Now if you see, here the dipole moment is in this direction, this is in this direction, equal in magnitude and opposite in direction. So they will cancel each other. Now here what happens? It will be having a net dipole moment. So this compound is polar, or you can say have a net dipole moment. This is non-polar compound, even though it has a polar bonds. Okay. Next is your hydrogen bonding. So for hydrogen bonding, what is the what are the conditions that has to be there? So the hydrogen must be attached to the electronegative atom. Okay, like oxygen, fluorine, and nitrogen. And there can be like two types of hydrogen bonding. One is intermolecular and intramolecular. Here you have to remember, if it is intermolecular hydrogen bonding, then the boiling point will increase. Because the molecules are strongly attracted to each other, we need more energy to break the bond. So in that case, the boiling point will increase. And if we have intramolecular hydrogen bonding, in that case, the boiling point will decrease. Okay, like two compounds are given in one, like for example, we have orthonitrophenol, okay, and paranitrophenol. Okay. Now if you see here this one can have ortho hydrogen like intramolecular hydrogen bonding, and here we can have intermolecular hydrogen bonding, right? So now if intermolecular hydrogen bonding will be there, then it is difficult to separate them and the boiling point will increase. So in this case, the boiling point will reduce. In that case, the boiling point will increase. Okay, so next is your valence bond theory. So what does the valence bond theory says? A covalent bond is formed by the overlapping of valence shell atomic orbital of the two atoms having the unpaired electrons. So when the valence orbitals combine, okay, then that is called as valence bond theory. Sigma bond is formed by head-on overlapping and pi bond is formed by sidewise overlapping. Here you should know sigma bond is formed from SS overlapping and SP overlapping. Pi bond is formed from PP overlapping. PX PX and PY PY, and here we consider as SPZ. So there is no hard and fast rule, but as a convention we take that PZ orbital is used for sigma bond formation, but not, no, it's like just a convention used. Okay. So how it looks, SS will look like this, SP will look like this, and we have PX. PX means it will look, so PX px can also form sigma bond. Okay, then if we have one more, we can have here one more sigma like this. This will be forming your pi bond, and we can have like this. This can form your 2 pi bonds. Okay. Now coming to hybridization. So according to hybridization, what happens? The valence atomic orbitals mix and form new hybrid orbitals. So number of atomic orbitals, this is very important, formed is equal to the number of orbitals taking part in the hybridization. So in your syllabus, you have 3 important hybridization: sp3, sp2 and sp. sp will give you tetrahedral, sp3 trigonal planar, and sp is linear. Here how questions are asked, they will give you a structure, carbon generally, and they will ask you to tell you the hybridization of each carbon, right? So like for example, so how you should know? For determining the hybridization, you should know that number of bonds, number of sigma bonds plus number of lone pairs. Okay, so what number is that coming? If it comes out to be 4, okay, then hybridization is sp3. If it comes out to be 3, then hybridization is sp2. If this comes out to be 2, then hybridization is sp. Okay, so for example, we have a structure like this. We can draw one structure like this. Okay, and you have to tell the hybridization of each carbon. Now you see, if this first carbon has 3 sigma bond, 3 sigma bond, 3 sigma bond means hybridization is sp2. This one is having also 3 sigma bond, so this is also sp2. This one is having 4 sigma bond, so it is sp3. Okay, like this you have to calculate. Next, coming to bond characteristics, this is very important. Here we have to discuss also how to find the bond order with a trick. Okay, so first of all, bond strength means what? Higher the amount of energy required to break a bond. Okay, now higher the bond order, higher will be the bond strength. So how to calculate the bond order? I'll tell you a trick. You have to calculate the total valence electron. Okay, total valence electrons. If the total valence electrons is 14, then the bond order should be 3. Okay, bond order. Sorry, not total valence electron, it is total electron. Okay. Okay. Now you have to, when you go on the other side, this value will decrease by half. When you go above 14 or below 14, the value will decrease by half. So 14 to 15, it will become 2.5. If 16, it is 2, 17, 1.5, 18, 1, 13, again 2.5, 12, 2, 11, 1.5, 10, 1. Now questions are asked, for example, you have to compare for N2, N2 plus and N2 minus. Calculate their bond order or bond length can also be asked. Now if N2 is there, N2 valence total electron is 7, like atomic number is 7, 7 plus 7, 14, so N2 bond order will be 3. Now N2 plus means 14 minus 1 we will do 13, so 13 bond order will be 2.5. N2 minus means, so I'll make it N2 2 minus, for example. So then what will there? 7 plus 7, 14 plus 2, 16, so 8 bond order will be 2. Then what is the bond order? N2, N2 plus and N2 2 minus. And next you have to see is very important, higher the bond order, lesser will be the bond length. So if the same thing we want to arrange in the bond length order, it will become opposite. N2 will have the least one, N2 plus and then N2 2 minus. Okay, so this is important, this trick you remember. Questions are asked from bond order, especially O2, N2, these are commonly asked. So just prepare this formula, try these questions, it will be very easy to solve and scoring. Next we come about molecular orbital theory. So according to molecular orbital theory, it is the linear combination of atomic orbitals. Okay, atomic orbitals are considered as wave functions here. So waves can have constructive interference and destructive interference. So if it is constructive interference, we get bonding molecular orbital. If it is destructive interference, we get anti-bonding molecular orbital. Next point you should remember is anti-bonding molecular orbital have higher energy than bonding molecular orbital. Now the electronic configuration you should remember, if it is like 14 or less than 14 the total number of electrons, then sigma 1s, sigma star 1s, sigma 2s, sigma star 2s, pi 2px, pi 2py, sigma 2pz, pi star 2px, pi star 2py, sigma star 2pz. Now if the number of electrons is like greater than 14, for O2 like 16 electrons are there, then the electronic configuration will change and we'll get sigma 1s. So everything is same. Here what happens, this one interchanges. Okay, we will get first sigma 2pz, then pi 2px equal to pi 2py. Other rest part is same. Okay, now from this one you can also calculate bond order. Bond order is half of number of bonding electrons minus number of anti-bonding electrons. From here questions are also asked to calculate the paramagnetic nature and the diamagnetic nature. Okay, so now we will see one small example for this one. Suppose you have N2. Okay, so N2 has 14 electrons. So we have sigma 1s, sigma 1 star 1s, sigma 2s, sigma star 2s, right? After that it will come pi 2px, pi 2py, right? So we can have pi 2px and pi 2py. So, and then we have sigma 2pz. Now you see 14 electrons, so I'll fill here 2, 4, 6, 8, here 9, 10, 11, 12, 13, 14. Okay. So now how to calculate the bond order? Bond order will be bonding orbitals. How many electrons are there? The ones with star are called as anti-bonding, and the one without star are your bonding orbitals. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, and we have 4 electrons here by 2, right? So that is 6 by 2, that is 3. Bond order is 3. Now how to tell magnetic properties? There is no unpaired electron here, right? So that is why it is a diamagnetic. So if there is no unpaired electron, then it is diamagnetic, and if there is unpaired electron, okay, then we call it paramagnetic. Okay. Now for example, we will write another example we'll take for oxygen molecule. Okay, so for oxygen the order will change here. So I will get here sigma 1s2, okay, sigma star 1s2, sigma 2s2, sigma star 2s2, then sigma 2pz2 will come. Okay, then we have pi 2px, pi 2py, 2, right? Now we have pi star 2px, okay, and pi star 2py. Now if you see till this one we have filled 14 electrons. 2 more electrons are left, 15 and 16. So for oxygen total electrons is 16. So if you want to fill the last 2 electrons, you have to fill like this. Okay, you cannot fill 2 electrons in one orbital. It has to be like if the orbitals are degenerate, then all the orbitals should be first filled before starting the pairing up, right? So we'll get 2 electrons here. So there is unpaired electrons, and as a result of which this molecule will become paramagnetic. And you can calculate the bond order using the same formula. Okay. Okay, so we have completed chemical bonding. Again, if I want to tell what are the most important topics that you have to revise, that is your Vesper theory, very important, molecular orbital theory, and then calculation of formal charges, and then you can practice Lewis structures how to do, but not many questions are asked from here, right? So just focus on molecular orbital theory, Vesper theory, and formal charge calculation. Okay, the key important things. Okay. Next, coming to the next chapter, which is very easy chapter, that is your classification of elements and periodicity in properties. Let us quickly revise this chapter. Some very basic things about periodic table we have to understand. So what we will understand first here, what is modern periodic law, how to write the IUPAC nomenclature for elements with atomic number atomic number greater than 100. Then classification of elements, and then periodicity in properties. Okay, so first one is according to modern periodic law, the functions of an atom depends on the atomic number. Okay, it is not on the atomic mass. According to Mendeleev law, it was according to according to the Mendeleev's law, the properties depend on atomic mass, but according to modern law, the properties depend on the atomic number. Next is why there is periodicity, because there is a similar configuration repeated over the time. And then there is in modern periodic table, it is based that the elements are arranged in the increasing order of their atomic numbers and not in the increasing order of their atomic masses. And next we have that there are 7 periods and 18 groups. N is the principal quantum for the outermost shell, and that tells which group the element belongs. And we have same number of electrons is present in the outer orbitals to find the electronic configuration. Okay, so these are some basic things you should know. 7 periods and 18 groups are present. Now coming to how to write the nomenclature of numbers greater than 100. For example, there is an atomic number of 1, 0, 3, right? So for 1, what is the name? That is un. Okay. For 0, what is it? Nil. Okay. And then for 3, it is tri. So U, N, and for 3, so the symbol will be U and T. Okay, like this questions you can just practice, very easy thing this one. Okay, now coming to the classification. So periodic table has 4 major groups, S block, P block, D block and F block. So S block is your from NS1 to 2 is the electronic configuration, right? And they are generally metals. Okay, and so here what should be the, one second, yeah, this should be generally metals, and which elements they belong? They contain your group 1 and group 2, right? Next you come to P block elements. The general electronic configuration is NS2 to NP1 to 6. They are generally metallites and non-metals, but some of them are also metals, and they consist of group 13 to group 18, 1 to 2, and that's it, 13 to 18. The middle part is your D block elements, which has a general configuration of N-1D 1 to 10 and NS1 to 2. Here, this is next we have, they are generally metals, and we have group 3D series, 4D series and 5D series, and they contain 3 to 12 groups. Okay, so you can see 1 to 2, then 3 to 12, and then 13 to 18. Okay, next coming to your F block elements, N to N-2, F1 to 14, NS2, N-1 P6 and N-1 D0. This is for your 6th and 7th period. So these elements are generally radioactive, and we have 2 series, 4F series and 5F series. Okay, so this is general classification of the periodic table. Now we will quickly go to the atomic properties or periodicity in the properties. First one is the atomic radius. Very simple thing. It decreases from left to right along the period. It decreases and it increases down the group. Okay, effective nuclear charge increases, so size decreases along the group. New cells are added, so size increases. Now what happens if you see in 3D series? This is given about 3D series, we have already discussed. So there is slight decrease from scandium to manganese because the effective nuclear charge is more dominant. Then iron to nickel, it remains constant because both the effects balance each other. And then if you see from copper to zinc, the size increases because the shielding effect is more than the effective of the nuclear charge. Okay, now so in the lanthanide series, what happens? There is a steady decrease in the size. Why? Because of lanthanide contraction due to the poor shielding of 4f orbitals. Okay, so you need to remember these 2 important things. Now coming to ionization energy. So ionization energy increases along the period and decreases down the group. Okay, now what are the factors on which the ionization energy increases? Atomic size. If the size is small, ionization energy will be more. Effective nuclear charge is more, ionization energy will be more. Penetration effect of the orbitals. So s orbitals are more inside the nucleus. So if you want to remove the electron from 2s and 2p, more electron energy will be required to remove from 2s because they are more penetrated or entered towards the nucleus. Then shielding or screening effect. If the shielding effect is poor, then ionization energy will be more. If shielding effect is strong, then ionization energy will be less. Then stability of half filled and fully filled orbitals. So if there is any half filled or fully filled configuration, then ionization energy increases. Okay, so like for example, if you see nitrogen and carbon, nitrogen and oxygen, right? What is the electronic configuration of nitrogen? 1s2, 2s2, 2p3. For oxygen it is 1s2, 2s2 and 2p4, right? Size is decreasing, oxygen is smaller than nitrogen along the period. So according to size, this oxygen should have more ionization energy. But you can see nitrogen has half filled electronic configuration, as a result of which the ionization energy of nitrogen is more than that of oxygen. Okay, so this exception you can remember. Same applies for phosphorus and sulfur. Now next one is your electron affinity. So electron affinity increases along the period. The tendency to attract electron, as the size increases, effective nuclear charge increases, so the tendency to accept electron increases and decreases down the group. Okay, now factors affecting here is again atomic size. So if atomic size will be less, more nuclear charge, more electron gain enthalpy or electron affinity will be there. If effective nuclear charge is more, then also more attraction will be there. Shielding or screening effect. If screening effect is poor, nuclear charge will be higher and the electron affinity will increase. Now coming to electronegativity. So in same as electron affinity, increases along the period, decreases down the group. Okay, Now, what are the factors affecting here? Again, atomic radius, effective nuclear charge, oxidation state, hybridization. So, what is hybridization? More is the S character. Okay. More S character, more electronegative. Okay. Now, for example, if you see sp3, sp2 and sp. So, here 50% is S, right? Here around 33% and here around 25%. So, more S character, so that is why the electronegativity of sp will be, carbon with sp hybridization will be higher. Okay. Fine. So, yes, so this was the complete inorganic chemistry that we have discussed. Questions, like you can easily expect 12 to 15 questions from these topics. Revise them thoroughly, note it down and do some questions from this. So, I hope you have found this video very helpful. Just, it's like one day, just take it and watch it completely and note down all the important points, all the exceptions, all the trends, and deblock what are the properties, physical properties, what are the reactions, preparation method. So just note down it everything and revise in 2-3, like 1.5 hour, like 2 hours, and the complete inorganic chemistry will be revised. So I hope you have found this video very helpful. Please like, share and subscribe our channel for further updates. And the PDF of this inorganic revision, the all notes will be available in our WhatsApp channel. The link of the WhatsApp channel will be there in the description section. So download it, revise it and then go for the exam. All the very best. Thank you.